Hey, so everyone, so welcome back. So hopefully everyone turned in their poster draft. The most convenient way was through Canvas, and so Tony is going to try and provide feedback on these and forward some to me if he has questions about them, but provide feedback sometime tonight, if not tomorrow. And then as soon as you get approved, please send them to Chris Coleman. The instructions are in the PDF for the project. And send them to him with a specific thing in the title, and then he will start printing them. He'll probably start printing some of them tomorrow, and they'll probably be in his office, which is in the front office. You might be able to go and check if you want to, but otherwise they'll be ready by at some point next week before the poster session next week, Wednesday. As far as I know, there may be some change of plans, but as far as I know, it will be kind of in this room and maybe in the lobby, but I might still move it. So I'll try and figure that out by Wednesday. There's a couple of other things going on. There's the school's trying to put together like a demo day or something. Not sure if it's going to happen, but it would be that day, and this would be like the last event of it. But we're like senior projects, some of them would get some booths that would happen like from 3 to 5:30, and then this would start maybe at 6 or so. So the time for the poster session is kind of like our official exam time slot, which is why it got that. We could potentially start earlier if people want to start at, say, 5 instead of 6. That might be possible. If there's a strong preference, please let me know. But otherwise, we'll probably start at 6 next week, Wednesday, and it'll probably be in this room and maybe in the lobby, unless I say otherwise. I'll try and finalize that soon. Other thing, homework 5 is being graded. That I think that might be done this week, it sounds like, which would be good. You'll get that back before the quiz number 2. Quiz number 2 is next week, Monday, so in 1 week. So content of quiz 2 is going to be everything in the class starting from regression. So starting from everything after the frequent items till the end of the class. So it's not cumulative. And so it should be like the first quiz about about the same length and about the same degree of difficulty, and that's going to be in here. That'll be the official last day of class. Then the final thing is homework 6. This is the homework on the graph section, which is mainly the Markov chain and stuff, and having to do with the PageRank algorithm type related things. So that I have due on also April 29th, which is Wednesday. Some people have said, well, senior projects are due then, and but we have to grade them before grades are due and stuff. And so I'd like to have it due then, but I'd like to be flexible. So one thing I thought of doing is we're going to keep that official due date of April 29th, so people who are ahead of the game get advantage of that. But I won't. But I'd say probably up until the next Monday, which I think is like May 4th or something. So like until May Day, you can turn it in with no penalty, but you can't do the bonus question. And the bonus question should not be too hard. So if you want to do the bonus question, or attempt it, you should do it by April 29th. If you need a bit more time, then you can do it till May 4th. Does that seem reasonable? Any complaints about that? No? Yes?
Can we do the bonus question by April 9th for the rest of the homework?
We will, if you turn it in by April 29th, we will grade that one, if it gets graded in time. So if it gets graded before you turn the other one in, then that'll be your grade. So So that's there's a risk there. Yeah. So if you want to turn the bonus, we'll grade that. You can get five points. Yeah. So if you can do the bonus, you probably have done most of the rest of the homework already. Is there another?
I forgot my question.
Okay. All right. Well, I'm glad that's taken care of. So, yeah. So okay, we're getting near the end of this semester. So yeah. One
Quick question about homework 6.
Yeah.
Do you want us to normalize all the answers because they all line up when I normalize them between -1 and 1, or I assume if I normalize them between 0 and 1, but.
Yeah, so there's some weird things. So if you use the eigenvalues, you can get negative values. So eigenvalues are correct up to a sign, right? So if you multiply by -1, it gives you the same thing. But you should know they should be all positive. So if you're getting them all negative, then multiplying by -1. If you get some negative, some positive, that's probably something weird going on. Yeah.
I remember my question now. So
Okay.
Can you update Canvas to reflect that in the or update
Yeah,
the
so-
website to reflect that in the assignment?
Yeah, I'll write that on Canvas in the assignment. I usually do that after I discuss it with the class. Is usually what I've done. So I'll try and do that tonight, hopefully, if not tomorrow. Yeah. Any other questions? So okay, great. So I said we're getting near the end of class. 2 lectures left. We're gonna continue talking about graphs, but move away from the Markov chain and PageRank view of things, and talk about today will kind of be a potpourri of techniques, and basically the goal is to try and still haven't figured out how to write well in this thing. Okay. To find communities in graphs. Okay. Yeah. So let me just start over again. Okay. Community detection, right? So this is kind of like a large challenge that has kind of been floating around the community of data mining for a while. You can build the idea is that you have some data which is really some social network, or but somehow represented as a graph, right? So maybe this is the web graph, right? And so then a community is would probably be a subset of the nodes. And if you have a graph, the graph usually says something about a connection, right? There's a connection between the nodes. So you want a subset of nodes which is tightly connected. Okay, so that means there should be a lot of edges, right? So we've looked at something like this before, right? We've looked at clustering on graphs, right? So one way of doing this, you could think of doing is like the spectral, like doing spectral clustering, right? So this is one kind of way, but communities is kind of more loosely defined than that, right? So the idea is you have this graph. The node edge here, right? So this might be your graph. If you did spectral clustering, what you would say is this is one side and this is the other side, right? You divide it into 2 parts, and maybe you do this recursively. This should be one weird supernode. But with finding communities, the goal is to find some tightly connected subset. Maybe it's you found 2 communities here. It should include this node, right? So you found 2 communities here. These are both tightly connected areas, but not every node needs to be inside one of these communities. You can have nodes which are not inside of these communities, right? And in fact, you could say that, well, maybe this is all one community and it contains 2 other things in it, right? Or maybe another example, might be, so you might have a graph that looks like this, and then also have a graph that looks like this. And so what would happen is you'd have one community here, and then another one like this. And in fact, they would both contain the same vertex right here. So it'd be fine if one of the nodes is in multiple communities. Where in the spectral clustering formulations, you're typically dividing things, right? And each node is in exactly one of the subclusters. In communities, you're usually not as restricted on that. You'd say you just want to find these communities, and there's no reason someone can't be in multiple communities, right? So it could be that this one, if you're this person, maybe this one has to be that everyone is in the same church, and this one is they're all in in the same CS program in Utah, right? So these are all your friends from school. These are your friends from church. Maybe your friends from work. I don't know. There could be different groups, and you can be in multiple communities. You don't need to divide this up so strictly. Okay, so so this has been some question that has been posed given a graph structure. How do you find these communities in the graphs? This is a very old question, right? This dates back to these psychologists that have been studying this. I don't know if it's 100 years, but at least 50 years. Going back away. What's interesting though is that, so I've mentioned this to some of you. So like I'm not going to spell psychology right. Okay, so SY. So this has been studied in psychology. This is probably at least 50 years. So most of this data, though, was small, right? This was small data. And so the graphs had certain, these had properties that look like these graphs I'm drawing up here. They were small. They were often planar or not far from planar. There's a way you could draw them in such a way. So you can actually draw these graphs. They're graph drawing tools that work. And so the notion of what was a cluster was something, once you draw it, you can kind of see it. And then they tried to develop notions based on what they could see. But by small data, maybe this was maybe in the hundreds of nodes. These were always, these were mainly collected by hand. People would go out and they would ask people, or they would interview people, right? I don't know if you can imagine doing this nowadays, right? Now everything is online. We can somehow gather this data by crawling it online, or it's stored inside of our servers. In the boom of the .com in the 90s, right? So can you think of like some social network kind of companies from the 90s? What kind of social network companies were there?
AOL was with the
Maybe, yeah. So maybe AOL, right? There's this instant messenger where you had talked to friends that way, right? This was kind of a way of replacing the phone in some sense, maybe. But really, actually, what happened? There were a lot of companies that had thought of this. They had thought that there were these networks of people, and this would be where value was derived. there were actually so many companies, and this was maybe I don't know if this was a secret or not, but I talked to a few people who were around developing some of these companies. They said, yeah, so secretly, really what we want to do is build a network between people. We think we can drive value from this somehow. I'm not sure if they realized that was through advertising or through something else, but they wanted to understand the connection between people. There's this long history of people have thought that a lot of the development in all of the industrialized world was spurned by new forms of communication, whether it was railroad, whether it was telephone. These things kind of created new ways of building structure. Maybe it was email, and then they thought the next way might be a social network. This was floating around in the 90s, and then things crashed, and who knows what happened, and then there was like MySpace, and quickly that was taken over by Facebook, and now there's all these other things. There's Twitter. There's LinkedIn, and all sorts of other social networks are popping up all the time. Which ones are kind of are surviving is an interesting question. Which ones are building? Maybe Google Plus was interesting for a while. Maybe they're shutting that down. I don't know what's happening, right? But Facebook is one of the most valuable companies in the world. Part of that is they just have a lot of your personal knowledge. Part of it is they have this huge network of the connections of people. Okay, and what's interesting is that these networks are very different than these networks. These are going to be huge. Facebook has 1 billion nodes. So there are 1 billion users on Facebook, right? That's very different than hundreds. So these, if you try and draw these graphs, they look like what's called these hairballs. Okay, this is actually a technical term from graph theory. There are all sorts of weird technical terms from graph theory that are much less appropriate to be talking about here than hairballs, in fact. But they look like this if you try and draw them. There's this big connected blob in the middle that you can't make anything out, and there are a couple of things that they can pull off that don't have very much going on. So when you try and draw them, there's very little structure you can see most of the time. You can't use the old technique where you drew it, you said, oh, one group's over here, another group's over here. Sometimes you can pull that out. But it's often through these techniques that are very different than what was done here. There's often a lot of edges going between the clusters, but you somehow say, well, those somehow aren't important some way. And these are, so to get these are automatically collected. As with these edges here, maybe these are arbitrary because they were by an interview. Who knows how kind of precise that process is here. How you decide whether someone is an edge here is also maybe fairly arbitrary. Do you say if they're a friend on Facebook, is that it? If they follow each other on Twitter, is that enough? Or if maybe there are other ways of interacting other than by the strict friendship rules. So it's more vague of what exactly are these edges. Okay, this goes into a modeling. So all the discussion we had earlier in class on all these choices of distances and all these other things with the data, the same issue comes up here in building this network. This was one kind of history of these graphs. Through these psychologists, they collected this small data.coms, looked at this. Another thing that probably came in this area here was there was this mathematical theory of these random graphs. So the most famous of these was is what's called the Erdos-Renyi model, and this was basically every possibility of connecting two vertices by an edge was equally likely. Okay, so basically what it is for every pair of vertices. So these are basically defined by two parameters here. So basically, n equals the number of vertices, and p equals the probability that say vertex 1 and vertex 2 is an edge, right? So and this was independent. So every edge had an equal probability of being connected. And there's some very beautiful mathematical theory on this. They said as you increase this probability, what you do is you start to see these different components. You see one large connected component and a bunch of things off by themselves, and then a single connected component. At some point, you see cycles. And there's this nice mathematical theory about this. And so you either had these small data sets that you looked at or these models. But then when we collected this large data from these large social networks, neither of these fit. These graphs were completely different than what we had expected they were going to be. The math and the psychologists were kind of wrong. Or the psychologists there wasn't conclusive evidence on this. Okay, so let me start to kind of illustrate this by kind of posing what I think is kind of an interesting question. And this was something that was debated in the psychology literature, and there was no conclusive answer. So why do people join groups? Okay, so they phrased this. There were kind of two kind of competing theories. So let's say that there were. So let's start with some basic graph here, and there was some part here that's connected in the graph here, and let's say that. So let's say there's this part of the graph, and for instance, this part here is going to be this is like a known cluster. Okay, so now let's consider two new nodes. We'll say X. This guy is named Xander, I guess. That's an X name. Are there any other X names? I guess in China there are lots of X names, right? What? All right. So Xavier, Xander, are like Jing. Yeah. So there's okay. So but this one is named Xander. Okay. So Xander is not yet part of a group, but is connected to three people. And those three people are all connected to each other, okay? And then we have another Y person. What should be the Y person's name? Young. What, Young? How's that spelled? Y-A-N-G. Oh, Y-A-N-G. Yeah, great. Okay. So other person is Young. And so Young is also connected to three people in the group. But these three people... I've chosen poorly here. Hold on, I need to add someone else to my group. Okay. These three people are not connected to each other. Okay. So for Xander, all of his friends are also connected in the group, whereas Yang's friends are not connected to each other. Okay. So which person is more likely to join the group? Xander or Yang? Okay, so let's first start by voting. Who thinks Xander is more likely to join? Okay, and who thinks Yang is more likely to join? Okay, great. So we've got about 80% said Xander and about 20% said Yang, maybe. So, okay, so for the ones who think Xander, why do you think Xander is more likely to?
think common interest, because okay, so you would trust the other person because that person.
But they both have 3 friends in the group, so they both have the same maybe commonality of interest. That's all I know about them.
Or peer pressure to join, but all their friends know if they've joined the group or not.
So,
Whereas young wouldn't.
yeah, so we could say something about maybe there's a different form of peer pressure, right? So, any other? So,
There are 3 ways for him to join the groups. It's combinatory.
but there are 3 ways for both of them. They both have 3 friends in the group, right? So the count is not any different. So there's maybe different form of peer pressure. This one, so one of the arguments is that this one has a very tight community. So these 4 people are all connected to each other, right? It's a very tight community. You're more likely to kind of do stuff maybe all together. You do stuff with your tight community. But okay, but on the other hand, there's also an argument for Yang to join the group, right? I don't want to dismiss Yang, right? 20% of you said Yang was more likely. So what's the argument for Yang? Yeah.
If Xander was going to join, he would have done it a long time ago.
Yeah. So yeah. So he is. Okay, that's it's a good argument. I don't. It's more of so Xander. It's hard to write for Young. It's more of against Xander. So Xander would have before. Why wouldn't it be done? Well, maybe he would have, right? Well, maybe all of a sudden they met 3 new friends each, right? So they. I don't know. So there's kind of a variation on that, yeah.
If Young has a larger breadth view of the group, he might think, instead of just these 3 guys who only have the same 3 experiences, he's looking across the breadth of the group saying, hey, they like it, they don't even know each other.
Yeah, there's this broader view, or it's sometimes called independent support. So they're getting 3 independent views saying you should join this group, whereas this is some one united tight view. I have 3 friends, all come to me at once say you should join, versus 3 different friends at different times saying, yeah, you should join this new, you should join this new cult, that I'm in, right? Is the 3 friends at once more likely to get you to join a cult, or is it 3 different people coming up to you, to get you? It doesn't have to be a cult. Nothing against cults, right?
But doesn't the sort of the positive perception of the group, what if this is like a prison population and the guy in Young happens to be a prison guard,
Yeah.
Can we assume that this is a positive group?
Yeah. So it's I didn't think about that. As far as I know, I'd always seen it discussed in the positive, but I don't see why it wouldn't be the same for the negative, right? If you had 3 friends who are committing crimes together, right, and they wanted to bring you in, or 3 independent friends who each were going to rob a bank, would you be more likely to join? So yeah, so that that could be a similar thing. Yeah. Any other comment? Yeah. Over there.
I mean, just to take that example, I mean, if you're really looking at it, Young might say, well, I can get 3 times more profitable by doing, because I have 3 independent friends. It's just how you look at the situation and whatnot.
Yeah, I mean, sometimes there are these groups where they give you incentives to join, right? Get a friend to join, and we'll give you, $10 or something off your next purchase, right? Yeah, and then Yang maybe trying to scan the system and get 3 times as much, right? That's possible. Any other comments? Yeah. No, you had the same comment.
No. Like experiences three different views of the groups. It kind of goes along with this breadth thing.
Yeah, right.
A little bit on top of that, maybe the society would be more likely to recommend a young because they can have different paths to trace it into the group.
Oh yeah, so like if there's kind of one leader of the group, right? So let's say that this person is the kingpin and they need to invite you into the mob, right? And so this is a final decision maker, and if he trusts two independent people, it might be more than coming from this known clique of people, right? Yeah, I think this is again in the independent support, but now inside the cluster instead of outside the cluster, inside the group. But it's a good point. Okay, so let's stop. Let's now that you've heard some arguments both sides, let's vote again. Okay, let's see if people change their mind. So who thinks Xander is still more likely to join the group? Okay, and who thinks Yang is more likely? I think Yang may have gained a few votes, but Xander lost more votes than Yang gained. So a lot of people didn't vote. Let's try again. I want everyone to vote. Everyone to vote, okay? It's not that hard. At least 20% of you are wrong, so you're not hiding, right? So who thinks Xander is more likely to be in? Okay, and who thinks Yang is more likely to be in? All right, I think Yang definitely gained votes there. Okay, all right. So it turns out the answer is going to be Xander is more likely to be in the group. I tried to build up support for Yang, but but Xander is more likely. So this was a debate. There was no known answer. People didn't know how to answer this question in psychology. There were maybe some small scale studies, but depending on how you set up the experiment, people could show one way or the other. Then once we started having these social networks, we could easily test, right? We could set up an experiment and test this. And it turns out that Xander is much more likely to join the group than Yang. And this is known more broadly as the preferential attachment, where I don't think that, okay, where you're more likely to join the group if you have multiple connections which are each connected to each other, or it's often written down more simply as if you're more likely to have an edge between here if it forms a triangle than you are to have an edge here that does not form a triangle. But this is roughly the same kind of property here. So this preferential attachment is usually written about the triangles, but this is a kind of a similar property that has been tested for. Yeah.
So I do have a question about influence. So are we assuming that these are just edges between that form a tightly connected group? Are we assuming that there might be weighted edges, or for like influence? Maybe.
Yeah.
Is it this person is tied to a tighter community because he has more ties, or is it because of the influence?
So we're assuming that the weights are the same, but it's the tightness of the community that is making the difference. People are more likely to join tighter communities, and so you end up getting this tighter community structure. So if you go back to these random graph models with the Erdős-Rényi, that did not show any of this tight community structure. They did not have these individual communities in the graph, or they were probabilistic in nature, but they didn't happen that often, right? So, but you're much more likely to see these clusters and then some other clusters, and so you think you should be able to find these communities that they exist to some degree. We could measure that they existed, that you get more of these triangles than you would expect randomly under this old model of random graphs. These were the sort of things people were early on in like the early 2000s doing lots of cool experiments with, and a lot was discovered about this. And so instead of these models of like these Erdős-Rényi models of random graphs, there are other models of random graphs where you could kind of simulate these, where they had these sort of community structures. And the simplest one is every edge you added had followed some preferential attachment model. You're more likely to add an edge if the vertices themselves are connected to each other. So if you have this edge, or another scenario would be something like this. So now this one is more likely than this one, because this one forms two triangles instead of one triangle, right? So the tighter you can make a community by adding an edge, the more likely you are to add it. This maybe you can see differently than these other than this other problem, but this probably makes more sense intuitively. If I'd ask you this question versus this question, probably almost everyone would say this edge is more likely because if you have X, and Y here, and they're friends, through the mob, then they're more likely to meet, right? They have a common friend. They trust each other through some way. They're more likely to interact. Whereas this person may have no connection with this person. They'd have to match just randomly, right? Or it could be that all of the edges that we're seeing here are part of a common phenomena. Maybe these two people in this graph are not friends, but they're part of the same cult, or a club or something, right? And so they meet through the common activity. So that's why that's why they would become friends, because there's some underlying common activity, right? Okay, and so there have been other kind of studies. I'd read one about how if you look at two people in a graph and they have the same number of edges, so the number of edges of this vertex I is called the degree, right? So this degree is equal to 5, and then there's another person with the same degree, but a lot of these, but there are a lot of triangles. These nodes have friends with each other. So this is node J, J here, and so the degree of J is also equal to 5. But there are lots of triangles that involve J. J is more likely to be happy than I. Having a tighter community is more, or a less tight community is you're more likely to be depressed, apparently. So there's kind of studies that it's helpful to have these tight communities. I guess humans are more natural in that setting. And so this was something that we could measure empirically on these graphs. Okay. Okay, so all this is kind of from a psychological standpoint, is very interesting, right? But from if you're a company and this is your social network, you could also think, okay, this could also be opportunity for advertising, right? If you can advertise to maybe all these people have a similar interest, if you hit them up with a common advertisement, it may work well. Or if maybe you need to put a single advertisement in the group and you think it will percolate well inside of that group, right? There are different ways you could approach this, but if you can find this structure, you think there should be value in understanding and exploiting this, right? So there's been kind of this search to find these different communities within these large graphs. And we can't just draw them and look for them anymore. We need some automated way to do it, some algorithmic way to try and find these and to identify these communities. Okay. Okay, so let me mention a couple ways of doing this. And these kind of represent kind of different ways that are kind of very kind of popular notions of understanding this kind of some nice structures of these graphs. So I'll start with one which is you may not see as directly connected to understanding these communities, but you can derive it from this. This notion is called Betweenness. Okay, so when you get a new area, you can invent all sorts of cool new words. So this seems it's a cool word. So if you have an edge, So if you have an edge A, B, then you say the betweenness of A and B is going to be the number of shortest paths in the whole graph that go through this edge AB. Or these are uppercase AB. Okay, so if we were to draw a graph, so which edge here is going to have the highest betweenness? So probably this one in the middle here, right? So if I wanted to find, so for instance, so by all shortest paths, I mean I'm going to start with every vertex V and find the shortest path to every other vertex. So this is U1, U2, U3, U4, U5, U6, and U7. So from V, I can define a shortest path to every one of these other vertices. And the ones for U4, U5, U6, and U7 all have to go through this edge. Okay, the ones through U1, U2, and U3 don't, but that means over half of the ones from V go through this edge, and over half of the ones from U1 also go through this edge, right? Because anything that goes from one side of this graph to the other has to pass through this edge. So this edge is kind of very influential. If you want to connect these communities, you have to go, or these parts of the graph, you have to go through this edge. All right, so this is somehow an important edge. So in some sense. You can define betweenness for a vertex as well. You can think of the number of shortest paths that goes through a certain vertex. And that would be an important vertex in connecting the graph. Now this edge would probably not define like a community. This is probably a intra or this inter. Forget what those means. So let me just use a more standard English word. A between community edge, right? So that's why it's called the betweenness. This is between the communities. It's not inside of the communities, right? Whereas this edge right here, the betweenness, it's only the shortest path between U6 and U7. So it's part of this community. To go from V to U1, you don't have to go near that edge, right? So if we can identify these high betweenness edges, how would we then use this to find these communities? Yeah.
So does removing that edge makes the graph not connected?
Yeah, right.
So you look for edges you can remove that make it not connected?
Yeah, so that's right. So to find communities, remove the high betweenness edges, and so then the remaining connected components are going to be the communities in the graphs, right? So you have to choose some threshold, but just like a lot of other clustering algorithms. So this is more of a where you make the graph disjoint, whereas I said you didn't necessarily need to do that, but you could do that, and this is one way that finds as like a clustering algorithm that can also find these communities. Yeah.
These edges seem to be what would be returned by a spectral clustering. Typically.
So it's not necessarily the same as the spectral clustering. Yeah, so it's not exactly the same. So this spectral clustering there's slightly different properties that have to do with some flow of the graph, and this is shortest path. It's probably similar. I don't know of any formal connection. I don't think it's quite the same thing, but there might be some result that says some relationship between them. Kind of intuitively, it is. You're right. It is doing the same thing. So spectral clustering either depend on what you do whether you do the normalized cuts, then that has this bias towards having equally sized halves. And I guess this will kind of have that as well, because you want to have both a number of things on both sides of the graph, right? Yeah. So it's definitely intuitively it's doing something very similar. Except spectral clustering doesn't really give you a score for these edges, right? So detecting communities is not the only application of this, right? This edge here is really a facilitator. So these sort of the edges, or maybe the vertices which have high betweenness, you can think of those as being the ones that are really going between different groups. Those are the kind of tying this connection together, right? And these may be, perhaps these sort of people are the sort of people you want to do some targeted advertising with, right? These sorts of nodes have a lot of connections. They talk to a lot of different groups, so you want to target this, right? Or maybe if you're some sort of like oppressive regime, right? And you have these clusters that are scheming against you, some underground group, and you want to break up these groups from talking to each other, then you would try and break up these edges. You'd say, this is where they're passing information. I want to break this up, right? You could think of doing it that way. Or if you want to say, if you want to build a connection, you want to build a strong social network, you treasure these edges. These are the ones who are really connecting across the subgroups. You want to build more edges like these. You want to study how these were built and kind of replicate that process, right? So these turn out to be kind of very important in doing this and understanding the structure. But one of the challenges is, like, how would you compute the betweenness? Yeah, or have a thought on that? I mean, in some sense, it's very simple, right? For every vertex, so you have a for loop over all vertices, right? For all v in your vertex set, you do find all shortest paths, right? And then you would add a count to all edges, right? So you compute all these shortest paths, you add counts. You can do this. This is really slow, right? Remember, we want to do this on these huge networks that are maybe 1 billion nodes, right? So first of all, you're iterating over all vertices. And then you have to find a shortest path to all other vertices, right? So you can use something like Dijkstra's algorithm to do this in one pass, right? But it's still going to be very slow, and then you somehow need to count all these edges as you do this. And there are complications. There might be ties. There may be 2 equally short paths, right? If the paths are unit length, you're going to have a lot of ties, right? So technically, to do this, to count all paths, what you do is the shortest path builds like a DAG, right? So you start from some vertex V, and you go down to some other vertices, and they're pointing down to these other ones. And so what you do is you kind of build this directed graph from V, And then what happens is you walk back up. This edge gets a 1, this one gets a 1, and then as you're walking back up, now from this vertex going up, they have a count of 2 that have come into here, plus whatever else they've done. But now there are 2 paths, so this splits. So this one gets a 2, and this one gets a 2, because it gets half of this one and half of this one. And this is a 3, and this is a 3. Right, so you get these shortest paths just from V, and then you need to do that for all the vertices. Doing this at scale is kind of, people don't really know how to do that. There's some attempts to do this, but it's a pretty challenging problem. This seems like a really great property. People have computed this on graphs, and it seems useful, but they can't compute it on really large graphs exactly. And things like sampling the vertices or sampling the edges does not seem to work that well. So there's a lot of structure captured here. All right, so this is just kind of one of these approaches at analyzing graphs. Yeah.
Could you estimate the highest betweenness edge by, let's say, doing something like a weighted average of edges only between the highest degree nodes? So one node has degree 10, the other has 20, only looking at edges between them.
Yeah, well, so this might work, but I'm not sure. You could think of having a bunch of high degree nodes here. This could be even higher degree, and so then there's this one really strong high betweenness edge you think here, but then you could have this kind of all these other edges that have that are basically part of there are 100 edges here and 100 edges here, and they each has degree 2, and all the shortest paths along here go along this edge path here. So the betweenness here might actually be higher than here. So I'm not sure. I'm just kind of guessing. But it's an interesting idea, but I'm not sure if that will work. Yeah, and the central, somehow, I think the central node here will have higher betweenness than the ones kind of on the boundary of these long arcs. This is my guess of how this will work. But again, this is kind of, it's an interesting property. This one is kind of further away from the actual community that really helps to tie it together. So that's the intuition here. But this is kind of one of these interesting properties that I think people discovered when analyzing these graphs, these communities. Let me mention, so a completely different approach is called modularity. And so this is a direct attack, and this is kind of a formulation of what you think a good community should be, right? So you can define this for a subset C of the vertices in a graph, right? So this is a subset of the vertices, so basically modularity is often written Q of C is going to be equal to the fraction of edges in C minus the expected number of edges, or the expected, not number of, this should be the fraction of edges in C. Okay, so I can count the number of edges in C. I have a set of vertices, right? So I have, and this is my set C here, and then if I look at the edges, these are the edges in C. The ones that go on the boundary are not counted in C. Yeah, right. So only the edges which stay within C are counted. Okay, so you want to have a lot of edges in C, and so the ones that are counted are going to be these ones that stay inside of the group. not the ones that go outside the group. Okay, but so this is kind of pretty intuitive to define. So often what you do is you write down, remember we can write this graph as this matrix, this adjacency matrix, I, J, and so we say ij equals 1 if an edge, and so then you would say that this part here is going to be the sum over all I, all in C, J in C times Aij, right? So you look at all these edges that go between two things in C, and then you count all these. So this is the number of edges. You want to know the fraction of edges. It turns out you need to divide this by 4 times the number of edges to get the right thing. The 4 here is because an edge will be counted twice if you do this, because you're summing over I and J. So you can count the fraction of edges this way. Now the expected number of edges is a little trickier to define. So this is kind of what defines this modularity. There may be other ways of doing it. This expected is kind of like saying based on the Erdos-Renyi model, but is adapting to the degree distribution of the graph. So this part is going to use the degree information. So if I have vertices in here that have a lot of edges, then I don't want to say that they're likely to be in a community just because they have a lot of edges. I want to make sure that all those edges that they have are inside the graph, right? So we'll have the expected number of edges. We'd say the expected value of an edge, ij, is going to depend on the degrees, the number of edges of each of the vertices I and j. So it's going to be degree of I times the degree of j. And then it turns out you want to do divided by 2 times the number of edges. Okay, because you're counting an edge twice somehow. So it's the product of the 2 degrees of both of the vertices, right? So the rationale is that if you have 2, so you can have different sorts of communities. You have some that there are people who don't have a lot of friends. If you go on these social networks, maybe usually, I've asked this in the past, there are usually some people who have a huge number of friends on Facebook, and other people who have, maybe 20 friends I guess is a small number, right? So how many people are on Facebook? Okay, and how many people have more than 100 friends? Okay, who has more than 1,000 friends? Are you okay, no one have more than 500 friends. Okay, so maybe 500 would be a lot, right? But I've had people in the past who've had like huge number of friends. They just add everyone, right? So there are these people who have these huge number of friends. Or if you think of like Twitter, some Twitter accounts are followed by huge numbers of people, right? And then you have another vertex that, so if these both have a lot of friends, then it's more.
From the group who think that they have 1,300 friends.
Oh, okay. So one of the remote students has 1,300 friends, right? So good. I'm glad we have some very some very popular fellow. So if this person has 1,000 friends and there's someone else who has 1,000 friends, well, you think, well, that's more likely that they're going to have an edge than people who have 3 friends, or let's say just 50 friends, right, and 50 friends, right? These people are less likely to have an edge. So you don't want to penalize these people for being in a community just because they're not quite as much as adding, adding people on Facebook very, very easily. No, there's no right or wrong way to do Facebook. So this algorithm is not judging, right? It's one way to think about it, right? Now if you think of this from the sense of a community, right? If I have a group of these vertices, then I'm kind of looking at, so then the modularity is the Q of C. And there's sometimes people write this slightly differently based on how you normalize these things. But they'll write it as this one normalizing constant, the sum over I in C, sum over J in C, Aij, minus the expected value, Ij, right? So you sum over the true edges minus the expected edges, right? So if you have a graph that looks like this, it's connected, and there are maybe only a few outgoing edges. So maybe there are 1, 2, 3, 4, 5 edges inside. This is more of a community than, let's say I draw this other graph. It'll have 1, 2, 3, 4, 5, 6. Okay, I have 6 edges inside here. I have 1, 2, 3, 4, 5, 6 edges here. So this is inside. But then these people also have tons of other friends. Right? They have lots of other friends on Facebook. So each of these people has a huge number of friends. Then these people could have friends. They could be friends with each other. They could be the same person. This is less of a community than this one, right? There are only 2 outgoing edges. So of all the edges which are of these nodes, most of them, almost all of them, are inside of this community. Whereas this one, most of the edges are going outside this possible community. So the modularity value here should be much smaller than here, right? So you want to make this modularity large. Okay, so in general, we're going to see that the modularity is going to fall in between, it's minus 1/2 and 1, and usually if it's between 0.3 and 0.7, your mileage may vary. This would be maybe a strong community. Right, so if you had a community, you thought, you want to say how tightly connected is this? This modularity gives you a way of quantifying this. Okay, so it gives you a score saying how tightly connected is this community, and that's relative to the degrees of the vertices. Right, so it's not judging based on how many friends you have. Right, so now for people like this, they probably have to be, for there to be a real community, they're usually in much larger communities, because if they have a lot of edges, in order for them to all make up, they probably need to be in bigger communities. But people with lots of edges the communities they're part of tend to be bigger, whereas people with small number of edges may be in much smaller numbers of, much tighter knit communities. And this algorithm doesn't really, or the score doesn't really judge. Okay. Yeah.
I have a question. It's kind of tangential to this. We're talking mostly about social networks and graphs and whatnot, but can you give any examples over the nodes to talk about for predicting trends as they might happen, and how one might model an environment to predict the trend based upon modularity and betweenness?
Yeah. So so this is kind of this is something that you might be able to use these community structures for. The trends you'll have some kind of some information will spread very quickly within a tightly knit community, right? So you think if you're advertising for a new type of soda, and this person starts drinking and they tell all their friends about it, and they they have this reinforcement because there's lots of these other edges, right? An edge from one of these people might mean much more than an edge from one of these people, because these are the people they really trust. Each of those edges is worth more. So if you advertise here, it might get picked up within this community before it gets spread out. Where if you advertise to this person, this community is not likely the one that's going to trust it. These people with a lot of edges, they may be the people who are, they're always posting stuff all the time, right? So one more thing that they talk about, I tried this great new soda, that's noise to you. Where if this person says it, it really means something. That could be the case. Also, this notion of betweenness is maybe more powerful, right? And a vertex with more betweenness has connections to many different groups. So if they advertise it, maybe they're connected because a lot of people are listening to this person. They may be very influential. So think of, there are certain people on Twitter which lots of people follow, right? If Oprah says there's this great new book, everyone goes and buys the book, right? Oprah can do this, right? Now, Oprah is powerful in many ways, but there's this new wave of people who are powerful on Twitter and in these other contexts, right? There have been, some people it's not unheard of for people on Twitter or Facebook to get paid to recommend a product, maybe directly or indirectly. This happens, so I think like someone like Dr. Oz probably does this, right? It's probably he'll deny there's any evidence of that, right? Or someone like Gwyneth Paltrow has this huge following on various forms of social media and pushes various products, right? You can make a lot of money doing that effectively. So if you can build up your own network, you can do this. You then be influential. And you don't just want to build up these people randomly following you. You want to build a community of people who interact with each other. Like I believe, like the reason why Gwyneth Paltrow's has been successful is not just that a lot of people listen, but they kind of chatter with each other about it. They kind of they've been trained to think alike about these products. So when she says it, they will self-reinforce it because they're a community. They're not just these different people listening. I think it's a much stronger presence that way. And that's kind of related to this preferential attachment property and who's likely to join a group. This tighter knit communities have more effect. Right? So if you want to be an influential person who speaks to these communities, so you may want to find the community and then find who's sending messages outwards into these. Right? So it may not just be the community, it may be other information as well. This structure is nicer to think about because it's more cleaner and abstract, but when dealing with this information, there's lots of other kind of bits and pieces going on you need to pay attention to. Okay, so this is a cool concept. Again, I've defined a quantity that if I have a potential community in mind, I can calculate this, right? But often my goal is to find these communities. So I want to find a cluster or a grouping of nodes that has a high value of modularity. So how would I find such a cluster? So again, you suggested for betweenness, you could do spectral clustering, right? And often spectral clustering is often a first approximation again. People use spectral clustering because it's relatively efficient, right? You don't necessarily have to do these, remember, spectral clustering is built on finding the first eigenvector of a graph, of the matrix representing a graph, and then you kind of divide the graph based on this one-dimensional projection on it. Okay? But as we know, kind of if the graph is 1 billion by 1 billion nodes, we can't run this inside of MATLAB, right? But what's another way of finding the first eigenvector?
Power iteration.
Yeah, so power iteration, which is how we did found the score for PageRank, right? That was basically that was the first eigenvector of the full graph, not the Laplacian. But there's a similar way you can approximate the first eigenvector of the Laplacian graph, and so that allows you to get a first approximation of this. Once you do that, you may try and kind of greedily add or remove vertices from these clusters that you found, and you can kind of optimize this. But again, this is not something that computationally is very easy, but you can kind of try and kind of add or subtract edges or vertices one by one or in groups to try and find these clusters with the high score. Right. So this is there are various heuristic ways of doing this. You could probably, like try and invent your own way. And so for instance, so let me just, I guess we've time. So to find high modularity clusters. So often you want to start with maybe approximate eigenvector of the Laplacian. And so you can often do this with these power iterations, which we talked about, which are very similar to what we're doing with the PageRank. And so you can do this at very big scales. And then you want to, these will give you to decompose. You can then, before I do this, then you can do this recursively on the subsets. And so you can compute the modularity pretty quickly. So if the subsets increase the modularity, you want to keep splitting. If they're decreasing it, then maybe you want to stop. Okay, so recursively on the subsets that you split, and then you want to optimize. So they're kind of, I like to call, there are two obvious ways how to do this. There's what I like to call the greedy nibble, and the greedy chomp. Okay, so the greedy nibble is you add the one vertex that increases Q of C plus V the most. Okay, so for all vertices which are adjacent to your cluster, you consider adding them, you recalculate the modularity, and whichever one increases it the most, you add that. If none increase it, then maybe you would stop. Or you could say, I could remove a vertex that would increase modularity. So the greedy chomp is you find all vertices that increase Q of C plus V and add all of them, right? So you find all the vertices which individually increase it, and you add all of them together, right? This seems, so it's strange, these vertices, if you add two things which are not connected to each other, that might actually decrease the modularity doing both, right? So once you do this, you want to check if it decreases modularity, maybe you don't want to accept this move, and then maybe add half of them or something. This greedy nibble, this modularity is has lots of local minimum, this function. It's very hard to optimize. And this one seems kind of reasonable, but it doesn't get very far. It gets stuck really quickly where you can't add or remove anything. Whereas this greedy chomp will actually explore the search space of clusters much more quickly and much more broadly. It'll less likely get stuck in local minimum. So this one is better around local min. But it's a little bit more unstable. So, but these are just various, these are not. This doesn't guarantee you're going to find the best cluster or any good clusters. These are just heuristics. This is it's a hard problem to solve. But this is generally the pipeline people would use to try and find high modularity clusters. Okay, so I want to talk about one last kind of approach to finding communities. Small core communities. So if you were in high school and you had a bunch of friends who are really close and probably mean to everyone else, then what would you call this group?
Jerks.
Jerks? No. Well, yeah, but these were your jerks.
They're my jerks.
You're okay. So right. So you might call this a clique, right? A clique of people in a high school, right? It's the cliques did not have to be jerks, right? So you can be friendly cliques, right? But this is a clique of a social clique, and I'm not totally sure the origin of this, but I think it comes from the notion of a clique in a graph, and a clique in a graph is going to be a subset of vertices where for all I and j and c, there exists an edge ij in the edge set of the graph, right? So a clique in some graph V, right? So that means, so if you had some graph the clique, this was poorly drawn, but the clique would be, is going to be these four edges are going to be a clique, because these four vertices, because every possible edge between them is included in the edge set. Yeah.
That's not the same as saying it's complete, right?
So it's the same as saying it's complete, but this subgraph is complete. The induced subgraph of these vertices is complete. Is the same way of saying it. Yeah. So these cliques, these are very strong communities. You can't have more edges than they have. Maybe they have some outgoing edges. That's fine. I don't care about the outgoing edges. I just want these really tight communities where everyone knows everyone, right? So everyone knows everyone, right? So one thing about cliques is that unfortunately it's a classic problem that's known. It's NP hard to find the size of the largest clique in a graph, or to determine whether the largest clique in a graph is above or below some threshold. Okay, but the cases where this comes up, where it's NP hard, is very different from what social networks look like. Those graphs are actually fairly dense, where they're really hard graphs. In small graphs, cliques are pretty easy to find. Basically, you start, so for instance, all edges are cliques, right? We also know that all triangles are cliques. Okay, and so there's been a lot of work in enumerating all of the triangles in a graph. So this is actually now, it was kind of a classic problem, but it's in the last 5 years, last few years, it's really well understood how to enumerate or count all of these triangles. These are all cliques. Once you find the triangles, there are not going to be too many 4 cliques, probably. There are way more triangles than 4 cliques. So in fact, the number of triangles is probably much more than the number of 4 cliques. So what you would do is, for each triangle, you would check each each neighbor if it's a four-clique. So you do this for all neighbors of all triangles. This finds all four cliques. The number of four cliques is probably much less than the number of triangles. So when you repeat this, the most of the work is often in finding the triangles. Maybe it's finding all the four cliques. And then once you have the four cliques, you can find the five cliques and the six cliques and so on. The same technique. For every neighbor, check if it touches everything else in there. This will find all of the cliques of each size. And usually there aren't too many huge cliques. And the ones that are, you find them pretty quickly. You can refine this a little bit more using techniques from like the frequent item set, where you kind of knew you only had to check neighbors that themselves were part of a four clique. If they weren't part of a four clique, they could not be part of a five clique. So you can refine this more if you're a little bit more clever. And so these sort of approaches, you can find all the cliques pretty quickly. This is also a way to bootstrap looking for modularity or other sorts of clusters. You start with the cliques and then you look at growing these a little bit more. Another edge doesn't have to be connected to everyone to still be kind of roughly part of the group. So this is another kind of basic and fairly simple approach, and this actually scales better, and you can get, in practice, usually solve the exact thing, whereas modularity or betweenness is much harder to do. But the cliques typically don't get too big, right? But it's often a good starting point. So that's kind of a potpourri of things about finding these communities. The lecture on Wednesday will be about sparsifying graphs. So if you have a large graph, how do you get to a much smaller number of edges and still keep the structure? And this will be partially on like social networks, but also like road networks, and you use kind of similar and different sort of approaches for that. So, all right, so yeah, that's it. So hopefully you get poster feedback soon. Remember to send those to Chris Coleman after you get the approval from Tony or me.